Hey guys, welcome to the next video in the Newman projection set. This time we're going to be covering the energy diagram you saw since the previous video. We covered all the how we can rotate Newman projections, and that was a precursor we needed to be able to understand exactly how this energy diagram works, and in terms of like the stability of various conformations and all that sort of stuff. And so here's the diagram that you've probably seen before. All right, and so we're going to just dissect this graph together. But first, let's just establish what exactly the molecule is here that we're going to be using. So I'm just going to move this over. All right, and so this is just essentially converting a Newman back into the line structure. So I find it easier just to pick this one because it's the simplest one. Like you don't want to be doing anything with like the eclipsed ones. It's just kind of weird. All right, so let's pick the carbon here. I'm going to color code everything. That's going to be our center carbon. And the red is going to be that other carbon. Okay, and we have a CH3 coming out, an H and another H. And from the red we have those two hydrogens and that CH3. Alright, so let's see how this works. Start out with that carbon center, that the one right behind it. And so coming out of the blue center we have a CH3 group, and we had two hydrogens. And we also had two hydrogens in the red. Alright, so I just redrew it for clarity. Alright, and so how do we exactly go from a Newman back into the line structure? If you guys want to pause the video and give this one a shot first before you see me do it, feel free to do so. Alright, and so remember the principle of the Newman projection is that this is going to be like, let's say, one carbon, and then the red circle behind it is going to be, the second is going to be the carbon directly connected to it. And so I'm going to start out with drawing the blue carbon, right? Then we have a bond, and we have that red carbon. Okay? And so the way I'm going to redraw this Newman is I'm just going to rotate this essentially as if I'm grabbing that carbon and rotating it out this way. So the blue carbon is going to be rotated so that it's going to be to the right of that red carbon. And you could have done it either way, any way you wanted. I'm just going to do that because that's just what I'm picking. Alright, and so we have a CH3 planar to that blue carbon, right? It's coming straight up. And so we're going to draw it straight up with a single solid line, CH3. And we had two hydrogens. One is going to be coming essentially to the left over here, and one is coming to the right. And so how do we represent those? Well, this carbon over here is going to be is coming out to the left in the Newman. And so when we rotate it so that the blue carbon is in front, it's now going to be coming at us. And so that means it's going to be wedged. Alright, so that's going to be wedged. Draw that hydrogen. And now we have this hydrogen to worry about. And so that's just going to be coming out of the paper away from us now. And so we're going to have to draw that dashed. And I'm just going to fix this, clean this up. It's not working. Okay. Now let's talk about the red ones. We have a CH3 that's going to be planar because it's coming vertically in the Newman projection, and so it's going to be pointed downwards on the line drawing. Right, pointed downwards with a solid line because it's in the plane. And so now we have our two hydrogens. Okay, so we have our two hydrogens. This one over here, let's start with that one. That one is coming to the left in this Newman, and when we rotate it so that this carbon is in front, the blue carbon is in front, we're now going to have that hydrogen coming at us, and so it's going to be wedged. That was not good. And when we look at this one, it's coming, when we rotate this molecule so that the blue carbon is now to the right of that red carbon, we're going to push this hydrogen back in so that it's coming out of the paper away from us, right? So going behind that the piece of paper, and so it's going to be dashed. Okay, so that's our structure in the that's the simplest structure that we can draw. And remember, this is going to be that anti-structure because CH3s are opposite of each other, right? And that's going to be the most stable conformation. So we have a 4-carbon molecule, all right, and it just a good idea to practice Newmans. Even if the question isn't asking you to draw a Newman, it's a good idea to still get into the habit of doing it, just so that when the exam comes, you can do it relatively quickly. All right, and so now we're going to dissect this diagram. So I'm just going to clear this out. So let's take it from exactly the structure we started out, which was this one. Okay, and so if we look, it says that we see that these two CH3 groups, right, and these are anti from each other. That means they're furthest spread apart from each other, right? You see there's no overlap here of this CH3. So if I go like that, no overlap with the CH3. No overlap with the CH3. Okay? And so what we're going to do from here is we're going to examine what happens when we keep rotating everything by 60 degrees. Okay? So every rotation, remember from the last video, every Newman rotation is going to be by 60 degrees, really. Okay? So we're going to go from 180, let's go to 240. All right? So we're going to go from left to right in this diagram. And so if we look, what stays the same is going to be that center carbon, right? So if you look at the center carbon, we still have this CH3, we still have we still have that H, and the H over here. So they're actually rotating this this outer carbon. Okay, and so a 60-degree rotation, if we go from staggered, means we're going to now go to an eclipsed conformation. Okay, so remember, eclipsed conformations have a lot of overlap in terms of the atoms on the molecule. The more overlap you have in a Newman, the more unstable it is. And the way we look at instability is over here on this y-axis, right? We have a delta G. Again, sorry for any Gen Chem PTSD, but this stuff is connected. So contrary to what a lot of people think, Gen Chem does still play a role in orgo. And so the higher that energy is, the more essentially the more energy that atom contains, and thereby is more unstable. So in other words, the lower this molecule is on the y-axis, the more stable it is. So the lower energy it is, the more stable. So that's how we judge the stability of molecules, how much energy they have. Higher energy is unstable, lower energy is more stable. Okay? And so we go from a staggered to an eclipse conformation, and we're going to have this overlap over here. CH3 and an H have an eclipsed overlap. This CH3 and an H have another eclipsed overlap. Okay? And so that's going to cause this molecule to be a little bit unstable, and so it's going to be further up on the diagram. So what happens if we do another 60-degree rotation? Well, we're going to now go again back to staggered. All right, so we're going back to staggered. In this case, again, they're still just rotating that back carbon, so we can just look at it in terms of the CH3 over here, right there. So it's now going to be positioned over the kind of right there. So if you look, here it is now. So because this is staggered, it is now going to be lower energy than the eclipse conformation. Okay, and so because that means there's simply less overlap between the atoms, and so we're not going to have as much of a energy cost, you can think of it, compared to an eclipsed. But what is present is going to be this interaction right over there. That CH3, those groups are close to each other, and if you remember from the last video, that's called a gauche interaction. Gauche. All right, that is also going to add to the instability a little bit, but not nearly as much as an eclipsed conformation would. And so you can see that, if I just erase this a little bit, you can see that, hold on. If you look at the level of this energy diagram, this molecule right here with that gauche interaction, right, is going to be slightly higher energy than this, than the anti interaction. Okay, And so with them, you can reason that out, right? If the anti-conformation is going to have the atoms as far apart as possible and as few destabilizing interactions as possible, essentially everything else will have to be slightly higher energy. And that can also be, and we can also look at the interactions for each one. This has a Gauche interaction, and so that's going to add the energy cost of the molecule. This one doesn't have a Gauche interaction, and it's not eclipsed, okay? And so, and all the groups are as far apart from each other as possible, so that is as low energy you can get, or other words, as stable as possible. Okay? So, we go from, now we have this staggered molecule, we're going to do another 60-degree rotation, and we're going to now go to here. Okay? So again, they're just going to be rotating that back carbon over here, this outer circle. And so now we're going to have these groups, these CH3, CH3 eclipse conformations. All right. In the previous eclipse ones, we only had CH3H interactions, and same. So now CH3 interactions are going to be more destabilizing than, like, let's say a CH3H interaction. Why? Because if we just compare the size, right? So imagine this: we have this carbon, so carbon, hydrogen, that bond to some other carbon. We can just write it as R, a hydrogen, and that hydrogen, right? And now we have two of these interacting together, so they're going to be kind of close to each other, right? So we have some R, H, and then that H, right? So they're going to be interacting a lot heavier than, let's say, this with an H group. So if I had this R with just one hydrogen, there isn't going to be as much interaction between these two, right? And so that's why the larger your groups get, the worse the more destabilizing those interactions are. Okay, so all the examples you've seen thus far, we've had methyls and hydrogens, but in Newman questions on the exams, they can give you something like an ethyl group coming out. And so if we compare now a methyl, which I'm going to write as Me, versus a methyl, Gauche interaction, and a methyl versus an ethyl, which is a 2-carbon molecule, I'm just going to write Et, Gauche. The ethyl is bigger than the methyl, and so this one right here is going to be more destabilizing. It's going to be higher energy, okay? And so that's going to be the basic principle. And now the reason we only need to kind of look at essentially half of this diagram is because once you rotate this another 60 degrees, so 60 degrees, we're going to essentially come back here. Because if you look, these are angles, so 360 degrees is just a full circle. We're coming back to where we started. And so all these are exactly what we've already covered. They're just, yeah, they're just exactly what we covered. Like, look at these two. Compare them. We have a CH3H interaction and we have a CH3H interaction. Here we have a CH3H and a CH3H. They're exactly the same. Okay? And so that's why the diagram is mirrored. So that's why these two are the same heights. Those two are the same heights. And there's only that one down here. Okay? And so just pay attention. It's good to you got to understand the principle of this. There's a reason why these two are the highest energy ones, or more unstable ones, and it's because of that eclipsed methyl interaction. Okay? If you look at the other eclipsed ones, these two and these two, they're not as high energy because they only have, while they're eclipsed, they only have methyl hydrogen interactions, right? A methyl hydrogen versus a methyl interaction. The methyl is higher energy. So that's why these even though they're eclipsed, they're slightly lower than that one. Okay? And so you can think of this for the same principle as the staggered ones. right? If we compare this and this staggered with that, right? These two have a gauche interaction right there with those two methyls next to each other, and same over here. While this does not have that gauche interaction. So all three are staggered, but the difference between them is that gauche interaction. Okay? And that's just the principle. That's the principle of that energy diagram. And so, just to show you guys how this applies to your tests, they can either show you this diagram, and essentially they will give you a line structure, and they'll say, and so what they'll do is, if I clean this up, you guys can rewind obviously if you needed any of that, and they'll label each peak as like A, B, C, D, E, F, G. Chances are they'll only go like A, B, C, D, E. They won't go G and F. And what they'll do is they'll give you some sort of structure. So they'll give you like carbon, carbon, wedge, something dashed, like that. And they'll ask you to essentially whatever conformation is drawn now to pick which peak, which one of these, what peak it's going to be at on the energy diagram. And so if you look just very quickly, you can draw these out, but these two are opposite each other, so that's the anti one. So that'll be as stable as possible or further down on the y-axis. Whereas if they were to give you something like this, right? You can draw the Newman for this. I'm not going to be going through I'm not going to draw that Newman, but you can pause and try it right now. But you'd see that that's going to be an eclipsed conformation with two CH3 interactions, and so that's going to be the most unstable form of this molecule, and so they'll be at the top. So they'll be either like the A, choice A. But we do have an example problem I'm going to show you, and unfortunately for you guys, it does use some math. Right? Yeah, you thought there was no math in the orgo? Well, I'm here to tell you that there is, and this is as bad as it gets. It's going to be just adding a couple numbers together, all right? So no one needs to freak out. It's just going to be simple addition. They don't let you use calculator in the test, but you really don't need a calculator for these questions, okay? And so we're going to take this step by step. So let's read it. It says, using the chart below, estimate the relative energy of the following conformation of 2-methylbutane. Okay, so the first step in this question, before you even look at this chart, is to draw the Newman projection as shown by that molecule. Okay, so let's start out. I'm going to label this. I'm going to take that as the blue carbon. I'm going to take this is the red carbon. So let's go blue. So we have that planar CH3 group coming up. CH3. We have that wedged methyl coming out, and so I'm going to be drawing this with the blue carbon as the front carbon, okay? And so if I'm doing that, then that methyl, since it's wedged and coming at us, will now have to be to the left. That's going to be another CH3. And we have that dashed hydrogen. It's going to be an H. Then we have the red carbon. We're going to have that planar methyl. And we're going to have a wedged and a dashed H. And that's the Newman projection. So what they're asking is to estimate the relative energy, and so what we have to do is look at the chart, and for every interaction that we find, we need to add those numbers together. So let's look at what we have. So the first three, the first 5 of these are all eclipsed interactions, but the molecule is not drawn in the eclipse conformation, so we don't need to worry about any of those. So we just need to look at essentially those two. And so let's look. Do we have any methyl Gauche interactions? Well, right here we do. We have one right there. Okay. Do we have any others? Nope. These are just methyl hydrogen interactions. So we're not looking at those. We only wanted the methyl ones. What about methyl-ethyl interactions? Methyl-ethyl Gauche interactions. Well, we don't have any ethyl groups, right? We only have methyl substituents. And so we don't have any methyl-ethyl Gauche interactions. So all we actually do is just, we would have added up all the interactions, but we only have one here, and it's just going to be this 3.8 kilojoules per mole. And so that's our answer. The answer is going to be A. Okay? And so that's how they can ask you these questions. Now, I do want to make a note. I drew this molecule here with that, let's back color. I drew this molecule here with the blue carbon in front and the red carbon in the back. Now I'm going to clear up a huge misconception for Newman projections, okay? The wedge, whenever you see a wedged atom on a Newman on the line structure, does not ever mean it's going to be always, let's say, on the left in the Newman or always on the right. For some reason, every year, students think that wedge is always left and dash is always right, or vice versa, when converting from the line to Newman. That is that's not correct, and that could cost you pretty severely on the test. All right, so just to clear it up, I will draw this molecule now with the red in front. Okay, and so we start with the red, and we have the blue in the back. So let's do with the red. This red, that wedged hydrogen, let me make that better. That wedged hydrogen, since we're turning the red carbon to the front, essentially I'm going to grab that hydrogen with my hand and rotate it out this way in front of me. Okay, so that wedged hydrogen is coming up, and now, because it's coming out of the plane of the paper in the line structure, as we're rotating the molecule so that the red carbon is in front, it's now going to be coming out to the right. All right, that dashed hydrogen on that dashed red hydrogen, so now that one is coming out of the paper away from us, and since we're rotating so the red is in front, it's now going to be to the left. And we have that planar CH3 group. That shouldn't be any trouble for anyone. Sorry. Now look at the blue molecules, well, the blue carbon. So we have that planar CH3 group. Let's just draw that one in. It's always the easiest one to draw. And we have this wedged CH3 group. And so because that wedged CH3 group is coming at us in the line structure, and we're rotating it so that the red is in front, this wedged molecule is now, this wedge is now going to be coming out over here. And that dashed hydrogen over there is coming out of the paper away from us in the line structure. And when we rotate the molecule, it's now going to be coming out over here. Okay? And so that's how it is. And so it's essentially, these two right here, these two molecules, let me change the color actually. These two are what happens if I flip one of these completely around. So look, you see the CH3 over here in blue? I'm going to take this entire structure and flip it. Now that CH3 is on the right. And everything is going to be able to overlap when you flip it. Okay? And so, yeah, you can draw Newman projections either way. And so that's how you do that question type. And I will see you guys in the next video. If anything didn't make sense in this one, again, please feel free to email me or talk to a TA. You can talk to me either through Facebook, send me an email. My email's on the review page at the top. Or yeah, that's pretty much it. So in the next video, I will do another Newman example. I don't know if I'm going to do it with the energy diagram or anything like that, but it will be some Newman practice for you guys. And of course, there are the practice quizzes that, again, I highly recommend you do them. They're extremely similar to what the test will look like, and a lot of them I just took questions straight from old tests and put them in there. All right, so I would highly recommend that you do them because it's great practice, and my opinion, the best way to do well in Oracle was just practice, practice, practice. All right, and so good luck, guys. I'll see you in the next video.